So speaking of personal heroes, there is one more person I need to introduce before I'm done with my session as an MC, and other people are going to take over. It's the person that has really, has created the first DIY computer in this country, Yugoslavia, like back in the early '80s, and has really inspired a number of generations, that got into like computing, hardware, and is just, just a really unique character. Also, like, it's the person without whom this conference wouldn't really happen. Like he created the badge, but then he really went above and beyond. And as Chris kind of mentioned, some of this going from one prototype to a production. We kind of decided that we want to do 250 badges, and I really hope you were able to get your badge. At the last minute we squeeze in another 50 people somehow in, but we were kind of assuming that not everyone's going to show up, so there's going to be badges for everyone. We did make sure that whoever got a regular ticket is going to get a badge, but it feels like a few people may have left, that came in later, may have left without a badge. I really apologize for that. But we decided to do 250 of these, and then the supply chain issues really kicked in, and this person really spent, I think, like 2 months stressing about all these that you guys have with you. So you should definitely try and do something amazing with them. And so really, without further delay, I just really want to introduce a not just local but global legend, Mr. Voja Antonic.
Thank you. Thank you very much. Thank you, Alec. So let's start. For the beginning, we don't have to talk much about hardware for this badge. The hardware is quite ordinary. We have the LED matrix here. We have the LED matrix, which is the main part of the badge, and we have horizontal anode drivers and cathode drivers for that matrix, and that's all. That's quite simple. Besides, we have the infrared communication unit, which adds the new quality to that badge. You can while hacking that badge, you can form your own network, infrared network, or you can communicate via infrared terminal. We have that terminal here. Maybe you didn't see it. It's here. You can type in your own message, which you can download to your badge, and when you switch it to display mode, you will have that message running on the moving message display. You can do it here very easily. We have also the small hacking area here, which is just for your convenience. While you're hacking badge, you don't have to limit just to software hacking. You can hack it by hardware also. This area, we shall talk about it later. This area is shaped for accelerometer modules, and you can use it for some applications which employ that accelerometer. This is a schematic diagram. We don't have to talk a lot about it. I'll just mention just a few points. I've got a lot of questions. What is this resistor here for? Just please pay attention. This is the LED diode matrix. This is the cathode driver. And those transistors here are anode drivers. And this is one extra resistor. When you're in bootloader mode, when you have to load the software that you wrote, your own software, this matrix, multiplex for this matrix does not work, of course, because Bootloader does not support LED matrix. So we need only one LED which should blink just to notify that we are USB connected. This resistor here, via this port here, C2, supplies that LED, one of those LEDs. And now the question is, why is it connected to two cathode outputs here? It's the sad part of the story. It's a fairy tale for tonight. We shall talk about it later. It's a very interesting question. So there is nothing special about this schematic here. We shall talk about the details later. Now, display multiplex. You know how multiplex works. I don't have to talk much about that. You have anode drivers here, which is represented here just some rotary switch. You switch the first column, and you switch those cathode leads through those current limiting resistors for the first column. Then you switch off the first column, you switch another one, you switch the second one, and switch cathodes on those LEDs which should be on in that column, and so on. When you do that fast enough, then you will not see anode switching. You shall see just that it works just like it should. So instead of 8 times 16, which is 128 outputs, we need only 8 plus 16, which is 24 outputs. But it is still too much. That's why we have this driver here. It is a shift register, which can be loaded only using two port lines. So we have to employ only 2 ports instead of 16 ports, which is very practical. So now we need only 10 ports to drive this display. And when we are in bootloader mode, we have only this port, this one port, which switches on one of those LEDs. In bootloader mode, only one anode is switched on, supplies anodes, and when you switch this cathode driver here, we shall blink this LED here, and that's enough for bootloader mode. When you exit bootloader mode, then display multiplex works and everything is fine. So, what does it mean? You can have the frame buffer, which is 16 bytes long, which takes 16 bytes in video memory. And you have driver which runs this multiplex here in the background. It's transparent completely because it's in interrupt. And everything that you write into those 16 bytes of buffer will be displayed here on the display. One means LED on and 0 means LED off. So you have very simple interfacing with the display. Let's go on. Now, this is my fairy tale for tonight. I have to return maybe 3 months ago and to start that story just to explain why am I showing you this slide. We started in January. We thought that 3 months will be quite enough to prepare everything and to make the production for your badges. And yes, it was enough. I contacted the agency here, which organizes all that, which supplies the material, orders PCBs in China and orders also pick-and-place PCB assembly also in China. I contacted them and said, what do I need? And they said, yes, that's fine, yes. But the problem is that there are some holidays in China in the first half of February until 17th of February, and please contact us at February 17th, which is 1 month ahead. So we shall lose 1 month, but we have enough time. He said, yes, we have enough time, that will be no problem. Okay, we have 2 months still. Maybe that's too much, but we don't have spare time, but it will be everything okay. Okay. I said, well, can we order those parts from DigiKey? He said, no, there's no problem. We have plenty of time. Just contact us, please, at February 17th. So I waited for the whole month, asked them on February 17th, and he said, yes, that's fine now. They have just started to work, but they need a few days just to heat up. But everything will be okay. We have plenty of time. And I said, well, okay, but please, let's start today. No, we can start tomorrow because they are 8 hours ahead. Their working time is finished already, and we shall contact them tomorrow. And I said, well, please don't do it tomorrow, do it today, because if you contact them tomorrow, then they will start it the day after tomorrow. No, we have plenty of time. Okay. And that lasted for 10 days. 10 days of negotiations, and at last they ordered material, they ordered PCBs, and I've got the answer from DigiKey that they can supply us with those LED matrix blocks in 9 weeks. In 9 weeks. But we have 7 weeks until this meeting. And I said, it's too late. They said, well, it's just 2 weeks more. It's no problem. What's the problem? And you wouldn't mind if you came here and if I told you, I'm sorry that there are no badges. You wouldn't, I hope so. Yes. Okay. Then I said, well, forget about it. I'll find it somehow. If I find it in some other place. The problem was that King Bright, which produces those LED blocks, does not have it on stock, and they have to produce it, and they need 8 weeks for that. So I decided to try to find it somewhere at distributors, at European distributors. I'll shorten this talk, and I'll just say that after a few days of investigation, I found about 140 displays which are enough for 140 badges, which is not enough, of course. Those displays were common column anode displays. Column anode, that means that column is anode and rows are cathodes. What shall I do? What to do? I was in permanent contact with Chris Gamel, and we just thought, what shall we do about it? And then I got the idea. I said, well, maybe we can find common column cathodes instead of column anodes, and we shall have 2 different types of badges with column anode and column cathodes. When you look at them, you will notice no difference in them. Some of them are driven by column cathodes and some are column anodes, and big deal, that will be okay. So we managed to find, I think, total of 220, which is still not enough. Then we said, what shall we do? Maybe we can find some other color. So we found for 78 display blocks, it's for 38 badges enough in green color. That's why some of you have green displays. And we said, well, we shall tell that those are some special displays for special persons, and everything will go okay. Well, now you can see one small letter below the white buttons, which are reset and interrupt button. Some of them have letter A and some of them have letter C. That denotes the type of your display. Some are common anodes and some are common cathodes. Sorry about that. Half of you have common anode and half of you have common cathode displays. But we solved that problem somehow. The consequence was that we have two different types of PCBs. The component placing is the same, but only the tracks on PCBs are different. But everything works fine, except that you have two types of firmware for those displays. You drive them in a different way. You see it here. For common anode displays, you drive column by column. For column cathode, you drive row by row. So the software is basically different. Firmware is basically different. For common anode, you have to pick when you make the driver, which is here in kernel program. When you make the driver, when you write the driver code for common anode, you have to pick bit by bit from all 16 locations. And for column cathode, you have to pick byte by byte. But you have to calculate which byte you have to pick to send it to the anode drivers. But all the same, the effect is completely the same. You have a 16-byte buffer, and there is no difference between them. Both of those types are serviced so that you write your image is this buffer image, here is this image buffer here. And everything is the same. Even I made a small trick which will help me auto-detect which type of display is used. That's why we have two connections here. Common anode have this connection and common cathode has this connection. And in auto-detect process, the controller sets one anode here, one cathode here, sorry, and another cathode here, and reads through this line and through this resistor, reads the analog input here in C2. You see, in bootloader mode, this C2 is output. It blinks one of those two LEDs, this or this, depending on the type of your display. So you know when you are USB connected. But in all other modes, all modes except the bootloader, this is input. C2 is input, and it reads auto-detecting firmware, puts one output and the other output low, and then reads them here. But another problem is that you cannot read this voltage level. This voltage level here is just about 1 volt, 1.5 volts. It's in the forbidden area. You know that when you read digital input on the input port, When you read digital input, then you must have properly defined logic levels, not between those limits. But this output here, because if we supply the whole unit with 3 volts, and you have 1.5 volts voltage drop on those LEDs here, you have 1.5 volts here on this input, which is forbidden. You can't supply the microcontroller input with that voltage. That's why it works like analog input. Analog input can have any voltage you wish. So auto-detect firmware, auto-detect module just puts this and then this output low and reads their voltage levels, compares them, and then decides which display is used. That's why we have only one firmware for everybody. It's completely the same, and all the applications are the same for all displays, and it works fine. Now, there's a difference between PCBs for common anode. This is the letter that I've told you. This is A, and this is C. And the component placement are completely equal. Let's go on. Keys, you know, if you are doing your projects with microcontrollers, then you always have to save the microcontroller ports. You always need some more ports than you have on your chip, and you have to save them anytime. So that's why those 4 keys, those arrow keys down there, use only one port line here. It's even the programming port. It's programming clock line. When you use the in-circuit programmer, you have only one line here with internal pull-up resistor, and here 4 anode drivers lines are used to denote which one of those keys are pressed. We must have those diodes here, which are just an ordinary diodes. Because if you press 2 buttons, then you will short 2 lines on those anode drivers, and so you will get a ghost on the display. You will have 2 anode columns which display the same, which display completely the same image. And that's very simple. So we used those anode drivers outputs to drive 4 keys only on one input line. Those 2 buttons are separated. One of them is master clear, and another one interrupt key, which is used for switching on and off, and in some cases for switching in pause mode. There is infrared transmitter and receiver for communication with the outside world. Here, the receiver which is used contains the complete receiver module inside the chip. There is a photodiode here, amplifier with automatic gain control, bandpass filter, which is 40 kilohertz carrier, and demodulator, and output which we connect to the receive data input. and transmit data with one single transistor which amplifies the signal because it needs a high current signal for this infrared LED. So we can establish the serial communication, but we need the carrier frequency 40 kilohertz for this receiver, and this carrier is added here with this diode and this output which is compare output. It employs the internal compare peripheral which generates 40 kilohertz without any software intervention. So the whole infrared communication unit is transparent for your firmware. You don't have to take care about it. You use the port, the serial communication UART port, the serial communication port for transmitting data and for receiving data. And anything you want to transmit, you have just to write it in the transmit register. And when you get the message, when you get the byte from someone else, from some other badge, then it will appear in your receive register. So you have full control under the serial communication peripheral. And it's very easy to apply this software for communication. It's very easy to communicate with other badge. You will see. Power supply is quite simple. Some of those units can go to sleep mode, but some of them cannot do it. So we must have this transistor which switches off power supply, so when the badge is in sleep mode, it consumes almost nothing. So batteries will last a long time. The only thing that I have to tell you is about this. You have a USB on your microcontroller, this microcontroller, and this VUSB, there is internal voltage regulator for this VUSB, but for L-type, low power type, this internal regulator is bypassed. It's bypassed, and you have to supply it from external line. You have to shorten VDD and VUSB on L-types. If you use other types, if you use PIC 18F, not LF, then you have to cut the PCB here. Because there is internal regulator and you cannot supply it through this VUSB. You only need this capacitor here. So if you use it without L-type, then you cut it here. But all your badges are L-type, and don't worry about it. This is a prototyping area here for two possible accelerometers. If you want to connect them, those are ADXL345 and GY521. If you want to use them, you can just directly connect them here on those pads. It is marked on the USB, and you will have no problems about it. This is the area that you can place your accelerometers or anything you want. You have two ports here and a supply, which is switched by the transistor. So if you use this type of accelerometer, you connect it here. If you use this type, connect it here, and you need almost no wires for that. Connect them directly. This is the internal schematic diagram for accelerometer MPU 6050. If you use it, then this is internal diagram, which actually you don't need if you use it with no special requirements. There is one thing more which we have also here. This is infrared terminal, which is connected to PC computer and serial terminal. So you can type in any message you wish in this terminal here. You can type any message you wish and write it to your display. Download it to your display, and you will have the new message. Now it's the greeting message. By default, it's the greeting message, but you can download any message you wish. Just type it on the keyboard and press the button send on the screen. The only thing is that you have to type in your serial number as the header, so you won't disturb all other badges, because if someone wants to download a new message for his badge, he could change the messages on all badges here in this area. That's why we have the header. Your badge will recognize your serial number and affect the message only on your badge, not any else badge. Why do we need a bootloader here? Why do we use bootloader here instead of in-circuit programmer? Well, if you use bootloader, then you really don't need no in-circuit programmer. If you are a hardware hacker, you probably have such a programmer. If you use microchips PIC controllers, then you probably have this one. It's very popular. It's PIC Kit 3. You connect it to your programming port. You have it on your display, and you can program any firmware you wish. But you have to buy it. I think that it's about $50 price. And if you don't have it, you can use the bootloader. You can program it for free. You just connect the USB port of your badge. You download the bootloader program, which is free also. You write in your software, and your bootloader will program it for you. The only problem is that the bootloader consumes some amount of program memory. It's about 6 kilobytes. But it takes care not to program itself. You have to put some origin, which is 6 kilobytes from 0, and that's all. You have enough program memory it's 32 minus 6, it's 26 kilobytes of memory that you can use. The only thing that you cannot do is to write anything to the bootloader, and that's all. I hope that this evening we shall meet and try to hack this badge, to write some new software for it, or even to add some hardware if you wish on the prototyping area. But the main goal is to write some software and to use this display and the communication port also in the most creative way. You will use your bootloaders, and we'll see. Maybe we shall see some interesting programs and ideas. This is how you connect your PickKit 3 if you use it, but I shall repeat, you don't have to use it. You can use bootloaders also. This is, we have a bootloader which takes 4 kilobytes. We have kernel also, which takes 2 kilobytes. It's 6 kilobytes in total that you cannot use. That's why I told you that you have to use this origin, which is 6 kilobytes from zero in program memory. There is a special process for interrupt entry points. Here, you see. It's interrupt service routine vector, which is, if you programmed PIC microcontrollers, then you know that interrupt for high priority vectors is at address 8, and for low priority interrupts it's at address 18. It is covered. You cannot modify those addresses. So if you write your own interrupt service routines, you have to somehow to rearrange them, so to use some other addresses, jumps to your interrupt service routines. That's why it jumps here first to your area. This is your area. You can modify it as you wish, this area here. And it jumps first on this address here for high priority interrupts, and to this address for low priority interrupts. And then it gets back, then it jumps back to kernel interrupt service routine, which is main service routine, which services your display, keys, and sleep mode also, and serial code reception. And kernel also has some initialization here, but it never comes back. It executes it only once after reset. So your code is completely free. You don't have to take care about your display, about keys. You have all those services which run transparently for you completely. So you write your code. When you want to display something, you use the buffer area, 16-bit buffer area, and so you make your images or characters or anything on the display. Those jumps seem a little messy here, you see. Each time when a processor gets the interrupt, it starts the program starts execution from this address, then it jumps here, and then it jumps here. And that happens for 1,200 times a second. 1,200 times a second, it jumps here, and then here, and execute this. And after, at the end, it returns back to your program there where it was interrupted, of course. Seems a little bit messy, but in fact, it's quite simple. You just, if you write your own interrupt service routine, you just have to change this jump, which is here, to change it here somewhere in your code, and write your own interrupt service routine. This low priority vector jumps here and here, but it is not used in any way in your badge now. If you want to use it, you have to enable interrupt nesting and to use both high and low priority interrupts. I hope that it will not be too complicated and that it will be fine. If you need any suggestion, I'm here to help. Okay. what does this timer interrupt do? This is very simplified flow chart of this diagram. When it gets timer 0 interrupt, it refreshes display matrix, dependent of the LED block type, and tests if interrupt key is pressed, no, arrow pressed, no, just return. If it is pressed, then I will not go into details here. It makes some processing after which it goes to sleep mode. If you press your interrupt button while it is running, it will go to sleep mode. So your badge sleeps in interrupt. Your badge sleeps in interrupt. Maybe you think that it's a little bit messy, but no, in fact, it's quite simple. It's because you don't have to take care about it at all. Your program does not have to take care about sleep mode. Interrupt will service it. If you use kernel, of course, interrupt will use it, and you will have no further problems about it. When you press interrupt key again, then it will wake up and continue exactly where it was interrupted. Only one small suggestion, which took me a lot of time to. I thought that I have bugged my program, but in fact it was not bugged. It was one simple thing, which was I thought that it was undocumented in microchips manual, but in fact it was documented, but very poorly documented. So it took me a lot of time to find it. The problem is with those three registers. A and select A, B, and C, which defines your ports, your input-output ports. Will they be digital inputs or analog inputs? You have to redefine them. You have to change bits in those three special purpose registers, special function registers. So when you write something in those registers, you change nothing. And I was worried what happens. Then I clutched. This is your processor has the access and banked addressing modes, and normally all those special function registers are in access mode, but only those registers are in banked mode. That's what I didn't know about. Because access modes starts at F60 hexadecimal, and bank modes ends in 56F hexadecimal. Those registers are not in access area, which should be normal. They are in banked area, so you have to use the bank addressing mode. Please keep that in mind, otherwise you will lose a lot of time, like I did, and you will learn it the harder way, like I did, of course. Some registers which are handled in kernel. If you use kernel here, you must use those registers. Those are only, this is buffer. I was talking about buffer here. Anything you write in this buffer will appear on the display. But when you're in pause mode, then it will switch, the kernel will switch to this buffer, this special buffer, which is on another address. So you can prepare some pause message here. For instance, if you play Tetris on this application here, which you have, then it displays even the result, your score here, and some moving message upstairs. But when it's in pause, when this bit is set here, then it displays not this buffer, but this buffer. This is your spare buffer. You can use it as you wish. It is not displayed in any way, but if you do some animation, you can prepare your animation here and just move it in some high-speed subroutine from buffer to the main buffer. Those registers are very important for you. This is flag register, and this is key edge register. When you switch any key, one of those bits will be set. You have to reset it in your firmware, but one of those bits will be automatically set. That's what kernel, which is in interrupt, does. So when you press any key, one of those bits will be set. This flag byte is for some special bits. You have the explanation for each of them here. And this is brightness control. You can control the brightness for the display in your badge by writing some other value here from 0 to 15 decimal. 15, all ones. So you can adjust the brightness. If you want to adjust brightness now, kernel does that special adjustment if you press those two buttons at the same time. Press the left and right button at the same time, and you have brightness up and brightness down here on those two. That means when you press this and this button at the same time, you have to be smart with your fingers. This and this button, then this is brightness up, brightness down. And this register is automatically updated. And this is one more thing that I have to tell you. After the lunch, we shall have a special contest. This is some other contest. We shall have the hacking night tonight, where we shall have some prizes for best ideas and best programs or best hacks. And we have another special prize for some special task for you. We call it Bletchley Park. You know what Bletchley Park is? It's a place in England, north of London, where German codes during the World War II were cracked. Turing worked on that problem also, and he created the algorithm for cracking of those Enigma codes. That's why we call this task Bletchley Park. There will be 2 or 3 badges with special firmware. You will communicate it with them by infrared ports. So you have to write your own firmware. You have to write your own firmware, which will transmit data to one of those badges. They are equal. It doesn't matter which one you shall use. You have to write some word, and it will scramble that word, and it will display in 2 moving messages. One is in the upper row, and another one is the lower row. Upper row message is the raw message which you sent. It should be 8 characters long. 8 characters that you sent by your badge and your code which you wrote. In the lower row, your message will be scrambled in some way. Which way, that's up to you to solve. When you get the scrambled message Hackaday, you won the prize. there is only one prize. And you have to solve, to know which is the magic word that you have to write. It will appear on the upper row, and in the lower row you will get some other message which should be Hackaday. If you solve that problem, you will get the blinking congratulations message, and you will win a prize. That's all. Those badges will have addresses, their personal addresses. Those are addresses 1 and 2 for 2 badges, so that they don't get confused, so that we can use them in the same time, not to interfere each other. It will start after lunch, we shall have a lunch now, and after the lunch, those badges will be set here, and you can start hacking it. I repeat, you have to write your own software. It's not default function of your badge. So you have to employ your laptops or anything you have here to write your own firmware and to hack to win this contest. I ask you for one favor. We wish to take a picture of you here, but I ask you just to wake up your badges, to switch them on, wake up and show us here, and our photographer will take the picture of the whole audience. Please. Oh, it looks great. It looks really great. Thank you very much. You will see on the picture, it really looks great.